All right, let's jump right into this explainer. Today, we are unpacking the math of linear programming. Now, I know that might sound like something purely out of a computer science textbook, but it's actually a deeply practical method that helps us solve real-world logistical and business problems. We are going to see exactly how converting everyday constraints into geometry can literally unlock maximum profit. Imagine you're a business owner. You've got limited cash to invest, and you only have so much physical space in your warehouse. How do you scientifically prove the absolute best way to spend your money? You don't want to just guess or go with your gut, right? You want mathematical certainty that your business strategy is going to yield the highest possible return. Well, that is the exact problem we're solving today. Here is the quick roadmap for today's explainer. 1. The ultimate optimization problem. 2. Translating business into math. 3. Finding the feasible region. 4. The corner point method. 5. Unbounded regions and exceptions. And finally, 6. World War II and beyond. Let's get into it. Section 1. The ultimate optimization problem. The furniture dealer. So picture this specific dilemma straight from our source material. Our dealer is working with some very strict limitations. They have exactly 50,000 rupees to invest, and their storage space can hold a maximum of 60 pieces of furniture. That's it. They are choosing between two items, tables and chairs. A table costs 2,500 rupees to buy, but gives them a 250 rupee profit. A chair is way cheaper at 500 rupees, but the profit is only 75. The big question is, exactly how many tables and chairs should they buy to make the most money possible? Moving on to Section 2, translating business into math, defining the terms. What's really fascinating here is how we seamlessly translate physical objects into algebraic language. First up, we need our decision variables. Let's just use X for the number of tables and Y for the number of chairs. Now, here's a crucial reality check. You obviously can't buy -5 tables, right? So mathematically, X and Y must always be 0 or greater. We call these our non-negative constraints. Next is the objective function. Think of this as your ultimate scoreboard. It's the linear formula, usually called Z, that we're desperately trying to maximize. For a furniture dealer, it's all about profit. Since they make 250 rupees per table and 75 per chair, our objective function is simply Z equals 250X plus 75Y. We want to push that Z value as high as humanly possible. Finally, we have to establish our constraints. These are our strict, real-world limits written out as linear inequalities. Remember that 50,000 rupee budget? That becomes our investment constraint. 2,500X plus 500Y must be less than or equal to 50,000. And that warehouse limit of 60 pieces? That's our storage constraint. X plus Y has to be less than or equal to 60. Section 3. Finding the feasible region. Visualizing the algebra. Now, staring at lines of equations can get pretty abstract, so let's shift over to geometry. When we graph these constraints, every line acts as a strict boundary. The budget, the space, the no negative furniture rule, and that shaded area right there in the middle, labeled OABC, that's called the feasible region. It is basically a visual map representing every single legal business choice our dealer could possibly make. Let's be super clear about what this shape actually means. Any mathematical point inside or right on the edge of that shaded shape is a totally viable investment, a feasible solution. For example, 10 tables and 50 chairs fits perfectly inside. But step outside that shape and you've got an infeasible solution. It is mathematically and physically impossible. Try buying 25 tables and 40 chairs. Well, you can't. You'd completely blow past both your budget and your space limits. Which brings us to Section 4, the corner point method, finding the optimal solution. So, out of an infinite number of decimal points inside that shape, how do we find the absolute best one? We obviously don't have time to test them all. Enter the corner point method. It's this brilliant algorithm based on a fundamental mathematical theorem. If an optimal value actually exists, it will always, and I mean always, sit right at one of the corner points of our feasible region. We don't have to check the middle, we only need to check the sharp corners. Watch what happens when we test the 4 corners of our dealer's graph. Point O is buying absolutely 0 furniture, which gets us 0 profit. Point C, 60 chairs, nets 4,500 rupees. Point A, 20 tables, bumps it up to 5,000. But look closely at point B, exactly 10 tables and 50 chairs. When we plug that into our objective function, it mathematically proves this exact combination maximizes the profit at 6,250 rupees. Literally no other combination will make the dealer more money. All right, let's level up. Section 5, Unbounded Regions and Exceptions, when math gets tricky. Because let's face it, real-world problems aren't always neatly wrapped up in a box. Our dealer had a bounded shape. You could basically draw a circle around it. But sometimes, constraints create an unbounded region. This means the shape shoots off infinitely into space in one direction. And when that happens, a maximum or minimum value isn't actually guaranteed to exist. If you are dealing with an unbounded region and looking for a minimum value, a corner point might look like the lowest number. But since the region goes on forever, you have to run an extra test. You have to graph the objective function over the open half-plane, basically just to double-check that the region doesn't secretly dip even lower into infinity. You always have to verify it. And here is a really cool exception: multiple optimal solutions. Imagine doing all this math and realizing two different corner points give you the exact same maximum profit. Well, mathematically, if that happens, then every single point on the geometric line segment connecting those two corners is also a perfect optimal answer. It essentially gives the business owner a whole menu of equally profitable choices. On the flip side, sometimes constraints are just way too strict. If your rules actually contradict each other, the lines will never enclose a shared space. They just pull in opposite directions. When this happens, there's absolutely no feasible region, which means no mathematical solution exists. It is quite literally the math's way of telling you, hey, your business plan is impossible. Okay, Section 6, World War II and beyond, the historic impact. Now that we've got the math down, let's talk history, because linear programming literally changed the course of the 20th century. This isn't ancient Greek geometry. It was born in the intense pressure cooker of World War II. In 1941, mathematicians started formulating these exact types of problems to optimize military operations, basically minimizing costs while maximizing damage to the enemy. Fast forward to 1947, George Danzig invents the simplex method, which allowed early computers to solve massive, complex versions of these problems. This math evolved so fast and revolutionized industry so completely that its pioneers were actually awarded a Nobel Prize in economics in 1975. I mean, it's a real game changer. The source material actually opens with this brilliant quote from mathematician George Polya. It reminds us that math shouldn't just be about staring at someone else's equations. These tools are meant to be actively applied to the real, messy problems that we create and face ourselves. So I want to leave you with this to chew on. We just saw how to maximize a furniture business, but linear programming is used to optimize diets, global shipping networks, you name it. Think about your own life, your personal budget, your daily schedule, maybe a massive business venture you're planning. What complex physical constraints in your life are just waiting to be mathematically optimized? Thanks for joining me for this explainer, and I really hope you start seeing the world entirely through the lens of feasible regions and optimal corners.